Hi, welcome back to Harita Tech Learning YouTube channel. Today we are discussing about continuation of AXI protocol. In this video, we will cover remaining transaction attributes, multiple transaction, atomic access, AXI for additional signaling, and low power interface. Let's start with transaction attributes. In this chapter explains transaction attributes used for system topology and cache support. Section includes transaction types and attributes, AXI3 memory attribute signaling, memory types, mismatched memory attributes, transaction buffering, access permissions. Let's start with transaction types and attributes. Slaves are classified into two types. Memory slave, it handles all transaction types correctly. Peripheral slave works based on implementation defined access method. Unsupported access must still complete according to protocol. AXI3 memory attribute signaling. In AXI3, A cross cache 3 down to 0, it defines transaction attributes bufferable, cacheable, and read allocate, write allocate. Here, A cross cache of 0, it is bufferable. It asserted transaction can be delayed before reaching destination, mostly used for write transaction. A cross cache of 1, it is a cacheable. If low, cache allocation is not allowed. If high, cache allocation is allowed. Supports transaction optimization like merging writes or prefecting reads. A cross cache of 2, it is read allocate. It suggests cache allocation during read transaction used only when cacheable is high. A cross cache of 3, it is write allocate. It suggests cache allocation during write transaction used only when cacheable is high. Memory types. AXI4 uses A cross cache to define memory types and cacheable behavior. Read address cache, read channel, write address cache, write channel. AXI4 introduce updated memory type names. Same memory type can have different encodings in AXI3 and AXI4. AXI4 supports backward compatibility with AXI3. Multiple A cross cache 3 values can represent the same memory type. Defines bufferable, cacheable, and allocation properties. Helps to improve memory access performance. Memory type encoding table. Device non-bufferable memory. Write response must come after the final destination. Read data must come directly from the final destination. Transactions are non-modifiable. Reads cannot be prefetched. Writes cannot be merged. Transactions with same ID and slave must stay ordered. Ensures strict and reliable device access. 0001, it is device bufferable memory. Write response can come from an intermediate point. Write must reach final destination in a timely manner. Read data must come from final destination. Transactions are non-modifiable. Reads cannot be prefetched. Writes cannot be merged. Same ID transaction must remain ordered. For 0010 non non catchable, non bufferable. Write response come from final destination. Read data comes from final destination. Transactions are modifiable. Writes cannot be merged. Overlapping address with same ID must remain ordered. For normal non-catchable bufferable. Right, that is 0011. Write response can come from intermediate point. Writes must eventually reach final destination. Read data can come from final destination or pending write. Transactions are modifiable. Writes cannot be merged. Overlapping transaction with same ID must stay ordered. For 0110, write through no allocator. Write response can come from an intermediate point. Writes must reach final destination in time. Read data can come from cached copy. Transactions are modifiable. Reads can be prefetched. Writes can be merged. Cache looks required for read and write. Same ID overlapping transactions remain ordered. No allocate. It is cache allocation not recommended. For 1110, write through write allocate. Same as write through no allocate. Write allocation recommended. Read allocations not recommended. For write through read allocate, same as write through no allocate. Read allocation recommended. Write allocation not recommended. Write through and write allocate, same as write through no allocate. Read allocations recommended. Write allocations recommended. Write back no allocate, it means 0111. Write response can come from an intermediate point. Writes may not immediately reach final destination. Read data can come from cache. Transactions are modifiable. Reads can be prefetched. Writes can be merged. Cache lookup required for read write. Same ID overlapping transactions remain ordered. No allocate, it means cacheable allocation, cache allocation is not recommended. For write back read allocate, it means 0311. Same as write back no allocate. Read allocations recommended. Write allocations not recommended. Write back write allocate, same as write back no allocate. Write allocations recommended. Read allocations not recommended. Write back read and write allocate, same as write back no allocate. Read allocations recommended. Write allocations not recommended. Mismatched memory attributes. Multiple masters can access same memory with different attributes. Catchability view must remain consistent for all masters. In this, we have two types: non-catchable region and catchable region. In non-catchable region, all masters use A cross catchy 3 down to 0, it should be 0. In catchable region, all masters use A cross catchy 3 down to 2, it is asserted. Different masters can use different allocation hints. Normal non-catchable memory can be accessed as device memory. Bufferable memory can also be accessed as non-bufferable. changing memory attributes, stop all master's access, perform required cache maintenance, restart with new memory attributes, transaction buffering. It applies device bufferable, normal non-cacheable bufferable, write through memory, write response does not need to come from final destination. Writes must reach final destination in a timely manner. In read behavior, device bufferable, it is read from final destination. Normal non-cacheable bufferable, it is read from final destination or pending write through. Read from cached, copy allowed. Intermediate bufferable rules, read transactions must eventually move to final destination. Buffered data must not remain forever. Continuous reads must not block timeout. Matched writes must not stay indefinitely in buffer. Continuous writes must not prevent draining in final destination. AXI cross protection. Here we have 2 down to 0 for read permissions and write access permissions. A cross protection of 0, it is privileged region. In 0, it is unprivileged. And when it is high, it is privileged. A cross protection of 1, it is security level. When 0 means it is low, it is secure. If high, it is non-secure. A cross protection equal to protection of 2, it is access type. When 0, it means low, it is data access. 1 means it is instruction access. Used to protect against illegal or unauthorized transaction. Transaction data bit is only a hint, not always exact. Multiple transactions. In this chapter, it explains how AXI supports multiple outstanding transactions, describes out of order transaction completion mechanism, converts AXI transaction identifiers, explains transactions ID usage, discusses transaction ordering rules. It includes removal of write interleaving support. AXI transaction identifiers. AXI uses transaction IDs to identify separate transactions. Transactions with the same ID must complete in order. Transactions with different IDs can complete out of order. A single port can act like a multiple logical channels using IDs. Masters can send new transactions without waiting for previous ones. Improve system performance through parallel transaction handling. Slaves return the same AXI ID in response ID or read data ID responses. Transaction ID. Each AXI transaction channel has its own transaction ID. Different channels use dedicated ID signal for tracking transactions. Transaction IDs help manage multiple active transfers. AXI 4 supports extended ordering uses using AXI ID identifiers. It improves handling of parallel and order transactions. Transaction ordering. Different masters have no ordering restrictions. Same master with different IDs can complete transactions in any order. Read transactions with the same read address ID must return in same issued order. Write transactions with the same write address ID must complete in issued order. Read and write transactions can complete independently. Transaction ID help manage ordering across the AXI interconnect. Read ordering. Same read address ID must return in request order. Differable read address IDs. Data can return in any order. Read data from different IDs can be interleaved. Read data ID is response must match the read address ID. Normal write ordering. Write data should follow the same order as write addresses. AXI4 does not support write data interleaving. Most slaves expect write data in address order. Interconnect must maintain correct write order across masters and slaves. AXI3 write data interleaving. AXI3 allows write data from different transactions to be interleaved. Interleaving is supported only for different write address ID values. Same write address ID transactions cannot have interleaved write data. Atomic access signaling. When A cross lock 1 down to 0, it is access type. When it is AXI3, here 0 it represents normal access, 1 means it is exclusive access, 10 it represents locked access, 11 means it is reserved. For AXI4, 0 or 1, 0 means it is normal access, 1 means it is exclusive access. Low power interface. In this diagram, channel system request and channel system acknowledgement handshake. It is power down or power up handshake. AXI uses handshake signals for low power state control. Channel system request is sent by system clock controller. Channel system request low means it is request to enter low power state. Channel system request is high means request to exit low power state. Channel system acknowledgement is sent by peripheral as acknowledgement. When channel system acknowledgement is low means it confirms entry to low power state. Channel system acknowledgement high confirms exit from low power state. Both signals high, it indicates normal operation. Handshake ensures safe power state transition. Channel active signal indicates whether low power request is accepted or denied. Next one is acceptance of low power request. In this diagram, system clock controller drives channel system request low to request low power mode. Peripherals detects the request and starts power down sequence. Peripheral drives channel active low to indicate clock can be removed. Peripheral then drives channel system acknowledgement low to confirm low power entry. Channel system acknowledgement must go low at least one cycle after channel active low. Sequence ensures safe transition into low power state. Next topic is denial of a low power request. In this diagram, system clock controller drives channel system request low to request low power mode. Peripheral acknowledges by driving channel system acknowledgement low. Peripheral keeps channel active high to deny low power entry. Clock must continue running since request is denied. System controller must perform to exit sequence before retrying channel system request. High starts exit sequence. Peripheral drives channel system acknowledgement high to complete exit process. Exiting a low power state. Exit can be initiated by system, clock, controller or peripheral. During low power state, both channel active and channel system requests remain low. Driving either signal high starts exit sequence. System clock controller initiates exits. System clock controller drives channel system request high to request wake up. Clock is enabled again by the controller. Peripheral detects request and starts power up sequence. Peripheral drives channel active high to request clock signals. Peripheral drives channel system acknowledgement high to confirm exit from low power state. Peripheral state initiate exit. Peripheral drives channel active high to request clock restoration. System clock controller restores the clock signal. System clock controller drives channel system request high to continue handshake. Peripheral completes power up sequence. Peripheral drives channel system acknowledgement high to confirm exit from low power state. Channel system acknowledgement can remain low until peripheral is fully ready. I hope you understand. Please do like, share for more content.